Welcome to the Deep Dive, where we plunge into the fascinating, often invisible technologies that are quietly shaping our future. Today we're talking about the very airwaves we rely on for nearly everything. Wireless networks. Just pause for a moment and consider your digital life. We're constantly demanding faster speeds, connecting more and more devices from the smartphone in your hand to smart home gadgets, wearable tech, and even, the promise of autonomous vehicles communicating in real time. We expect seamless, instant connectivity wherever we go.
This future we're building, this interconnected world, relies on incredibly sophisticated foundational technologies, many of which we rarely even think about. But here's the
solution called Non-Orthogonal Multiple Access, or NOMA.
NOMA is without a doubt, a powerful concept for dramatically boosting spectrum efficiency. It represents a really significant departure from how we've traditionally managed wireless traffic. However, this power comes with a unique and, let's say, non-trivial challenge. Effectively managing the inherent interference that arises when multiple users quite literally share the same slice of the airwaves simultaneously. To prevent this organized chaos from devolving into an unmanageable mess, the network needs to constantly understand the specific
language, or, as we say in wireless communication, the modulation type of each individual signal flying through the air. Imagine trying to follow multiple conversations happening in the same room all at once.
Right? And that, dear listeners, sets the stage for our deep dive today. Our mission is to unpack the absolute cutting edge of how artificial intelligence is being deployed to automatically identify these wireless languages in complex NOMA systems. We're drawing our insights directly from a groundbreaking paper titled Modulation Classification for Non-Orthogonal Multiple Access System using a modified Residual CNN by Parmar et al. And you might be thinking, modulation classification, why should I care about something that sounds so deeply technical and specific?
Well, this isn't just academic theory or complex mathematical equations confined to a lab. This is the hidden key, the unseen hero, enabling your seamless video calls,
undeniable force driving innovation in wireless, the insatiable demand for bandwidth. Our current wireless networks are under immense, unprecedented pressure. We're talking about an exploding need for incredibly low latency inside. Imagine real-time gaming, remote surgery, or self-driving cars reacting in milliseconds, alongside requirements for high reliability, massive connectivity for literally billions of Internet of Things devices, and critically truly high spectrum efficiency. Just think about the sheer
volume of data being transmitted daily. From millions of people streaming high-definition movies, to smart city sensors communicating traffic flows, to industrial machines talking to each other on a factory floor. It's not...
You perfectly captured the scale of the challenge. It's huge. And it's precisely in this context that non-orthogonal multiple access, or NOMA, emerges as a remarkably promising and innovative solution to address that looming spectrum deficiency. What's truly innovative about NOMA is how it achieves this. Unlike traditional approaches where users get their own distinct slice of the airwaves, NOMA allows multiple users to quite literally share the same time, frequency, and power resources simultaneously. On the surface,
That sounds completely counterintuitive, almost like trying to have several conversations in the same room at the exact same time without any way to distinguish who's saying what. It seems like it would just create an unmanageable mess, right? A cacophony.
Okay, so if NOMA is essentially throwing multiple signals onto the same digital lane, how on earth do you keep them from crashing into each other? That really does sound like an unmanageable mess. This is where it gets really interesting. Unlike traditional orthogonal systems, where each user gets their own dedicated slice of the spectrum, think of it like having separate, clearly marked lanes on a highway. NOMA intelligently superimposes signals. It's less like separate lanes and more like having multiple vehicles driving in the same lane, but they're distinguished not by
physical space, but by how much power they're exerting. So how does the network keep them straight when they're all piled on top of each other.
It's all thanks to these carefully calculated power differences, indeed. And if we connect these to the bigger picture, NOMA employs a pretty sophisticated power allocation strategy. Imagine a base station communicating with users at different distances, or maybe with varying signal qualities due to obstacles like buildings or hills. Users with poorer channel conditions, we can think of them as the farther users, maybe physically further from the base station, or perhaps in a location with more obstructions that deliberately allocated higher transmission power.
Conversely, users with better channel conditions, the near users, get less power for their own signal. This isn't random or arbitrary. It's a deliberate optimization for fairness and reach.
Dictates the signal recovery process, which is where things get a bit more complex, especially for one type of user. For the far user, the process is surprisingly straightforward, almost elegant in its simplicity. Since their signal is transmitted with higher power, they basically just treat the near user's lower power signal as if it were background noise or static. They essentially filter out the weaker signal and directly extract their own strong signal. Fairly straightforward, like you said, they get the easy job. But the near user's challenge
is where the true complexity lies, and where our deep dive really kicks in, because they receive both signals their own, which is intentionally weaker, and the far users, which is stronger. They must apply.
Exactly. And to deep dive into SEC, just consider the precise steps the near user needs to take. First, they have to completely decode the far user's signal, even though it's not meant for them directly. Once they've successfully decoded it, they then regenerate that exact signal and quite literally subtract it from the combined received signal they picked up. This cancellation process is absolutely crucial for them to effectively isolate their own lower power signal from the stronger interference. It's kind of like being in a noisy room, right?
You have to decipher the loudest conversation, mentally reconstruct it, and then actively tune it out so you can finally hear the quieter person you actually want to talk to. But here's the fundamental catch that drives our
So if that modulation type is absolutely critical for the new user to perform SIC, how does the system actually get that information? Does the network just, tell every user explicitly, maybe setting a little flag saying, hey, that color signal you're trying to cancel, it's using BPSK, or L116 QAM? And if so, wouldn't that create a whole new set of headaches? Seems inefficient.
You hit on a crucial point there. Sending that kind of explicit modulation information as a separate, dedicated signal introduces significant overhead on the network. Think of it as valuable data that isn't actually your content, it's just instructions about the content. It's like adding extra empty lanes to an already congested highway just for communication about the cars themselves. This consumes precious spectral resources that could otherwise be used for actual data transmission, making the system less efficient and potentially slower.
And this is precisely where automatic modulation classification, or AMC, steps in. AMC aims to automatically identify the modulation type of a signal without any additional signaling or explicit instructions.
Right. So before we dive into the brand new cutting-edge solution proposed in this paper, let's take a moment to look back at how automatic modulation classification has historically been done. The vast majority of early AMC methods were designed for orthogonal multiple access, or OMA, systems for those separate dedicated lanes on the highway we talked about. In OMA, there's no co-channel interference from other users occupying the same frequency at the same time. That's a fundamentally different and frankly much simpler scenario than the complex superimposed signals we find in NOMA.
It's a bit like trying to classify vehicles on a clear, empty road versus a multi-car pileup, isn't it?
It really is. And these traditional AMC methods, largely developed for that simpler OMA environment, can be broadly categorized into two main types. First, we have likelihood-based LV methods. These are highly probabilistic approaches. They analyze the received signal and calculate the mathematical likelihood that it corresponds to various possible modulation types. They're like highly sophisticated signal fingerprinting systems trying to match the received signal against a library of known patterns. for a small number of
modulation types and at high signal-to-noise ratios, SNRs, meaning very clear, strong signals with minimal interference, they can be quite effective. However, their performance tends to
these methods take a different approach. Instead of complex probabilities, they work by first extracting specific, predefined characteristics or features from the signal. Think of these as measurable attributes like the signal's statistical texture, its repeating patterns, or maybe its energy distribution across frequencies. Once these features are extracted, often through techniques like analyzing cyclic spectrums or higher-order cumulants, which are essentially advanced statistical measurements of the signal's waveform, they are then fed into more traditional machine learning classifiers like support vector machines, SVMs, or decision trees
to make the final modulation decision. These generally have lower computational complexity than the LB methods, making them a bit more practical for some applications.
Okay, but here's a critical insight from the research paper we're discussing. While many traditional machine learning algorithms like naive Bayes, k-nearest neighbors, KNN, or SVM have been diligently applied to AMC over the years, the existing literature clearly shows they were often not feasible for the demanding requirements of modern AMC, especially in dynamic, high-interference environments. My intuition suggests that manual feature engineering, that painstaking process of deciding what features to extract, is incredibly brittle.
If the environment changes or the noise patterns shift, those handcrafted features might become useless. Is that part of the reason they struggle to deliver the accuracy needed?
You've hit on a core reason, and it's a brilliant observation. Yes, exactly. Manual feature engineering is indeed brittle. It requires deep domain expertise to identify the most discriminative features, and those features might only be optimal under specific, often idealized conditions. When the environment changes, as it constantly does in wireless, those handcrafted features may no longer capture what's essential, leading to a significant drop in accuracy. These traditional approaches simply couldn't learn the subtle, complex, and often nonlinear patterns
that differentiate modulation types, particularly when signals are distorted or superimposed. They just couldn't achieve the near-perfect signal identification required for robust next-generation wireless.
Those traditional methods that require manually designing and extracting features, DL models can automatically learn and extract incredibly intricate features directly from raw signals. They do this much more efficiently and often with far greater accuracy and robustness than those older hand-engineered methods. They essentially learn what features are important rather than being told. It's a big shift.
And the examples of deep learning models applied to AMC and OMA are plentiful, truly showcasing the versatility of these networks. We've seen basic convolutional neural networks for CNNs, which are excellent at recognizing patterns, almost like a powerful visual system for signals, showing much better accuracy than traditional machine learning approaches. Then, long short-term memory, or LSTM, networks which are particularly great at handling sequences and temporal data, remembering patterns over time were proposed, and sometimes even outperform CNNs.
To get the best of both worlds, hybrid CNN LSTM models emerged, specifically designed to learn both temporal and spatial features within the signal simultaneously. Researchers even got incredibly
Exactly. And then feeding these pictures into powerful pre-trained CNNs like GoogleNet and AlexNet for classification. Furthermore, advanced training techniques like two-step training and transfer learning were employed to significantly decrease the time required to train these often massive, complex models. It was a true deep learning arms race in the OMA space.
This raises an important question, though, and it's the core reason for this paper's significance. If deep learning has been so incredibly effective for AMC and OMA systems, why is NOMA still such a significant challenge that this paper specifically addresses? The crucial point, the fundamental difference, is that almost all these advanced deep learning methods for AMC do not consider or are not trained to handle the unique interference conditions that arise from co-scheduled users, which is a defining characteristic and inherent challenge of NOMA. Because because they weren't
designed to untangle superimposed signals, these OMA-focused DL methods are simply not directly applicable, or at least not optimal, for NOMA systems where signals are literally
Yeah, that makes sense. And this brings us to a really stark observation made by the authors of this paper. Before their work, the landscape for automatic modulation classification, specifically in NOMA systems, was surprisingly sparse. Despite NOMA's growing importance in the wireless landscape, the authors explicitly note that, to their knowledge, only one existing method had specifically performed AMC in NOMA, and that was based on fourth-order cumulants, which the paper referred to as the CD method. It almost sounds like a forgotten corner of research.
It truly highlights a critical void, a significant research gap. Despite the growing importance and promise of NOMA for future wireless networks, there was a clear, pressing need for a robust, deep learning-based solution specifically tailored for the highly unique and challenging interference environment of NOMA systems. The existing method, while functional, just couldn't provide the level of performance needed for next-generation systems, especially in noisy conditions. This is precisely what the paper we're discussing today aims to provide.
a cutting-edge answer to a fundamental and previously underserved problem in next-generation wireless communication, moving the needle significantly forward.
Okay, so with this clear gap
It is. Let's break down its intricate components because the ResCNN architecture is indeed specifically designed to handle the complexities and inherent interference of NOMA signals. It's built with a sequence of intelligent processing layers. First, you've got 4 convolution layers. These are the core feature detectors, acting much like specialized filters. They scan the input signal, identifying patterns, and extracting increasingly abstract representations. Think of them as sophisticated pattern recognizers that learn to spot the unique fingerprints of different
Modulation types. Then, there are 2 average pooling layers. These layers are strategically placed after certain convolutional layers. Their job is really to reduce the spatial
Exactly. Then 3 dense layers, also known as fully connected layers. These are at the tail end of the network. They take the highly refined features extracted by the convolutional and pooling layers and perform the final classification. They weigh all the learned patterns and connections to make the ultimate decision about the modulation type. And crucially, the true innovation at the heart of the design, 2 modified residual blocks. These aren't just any standard building blocks. They are the innovative core that allows this network to be so effective in a NOMA
environment designed to overcome the specific challenges of superimposed signals.
Okay, but before any of this advanced processing happens, how does the raw signal even get ready for this network? It sounds like it needs to be in a very specific format. The signal, which is essentially a wave, has 2 key components that allow it to carry complex information: an in phase, a Y, and a quadricular Q part. Think of them like 2 separate but intertwined streams of data that together capture the full shape of the signal at each moment in time. So, this is why it's first represented as a 2x image with 2 rows, one for I, one for Q,
stretching across n time samples. But then it gets reshaped into a 2x n by 1 format. For those of us not steeped in neural network architecture, how should we visualize that input?
That's a great analogy, actually. Yeah, it's like giving the network a very specific kind of grayscale image. The 2xn matrix captures all the information, but neural networks, especially convolutional ones, often expect data in a certain channel format, similar to how a color image has red, green, and blue channels. Reshaping it to 2xn by 1 essentially treats the I and Q components as 2 distinct rows or features within a single channel. This specific format is what the initial convolutional layers are designed to efficiently process,
Extracting patterns across both the I and Q streams simultaneously. It's really about structuring the data in a way that the network's processing units can best understand and extract meaningful features from.
neurobiological neurons activate or don't. For the very final output layer, which has 4 nodes corresponding to the 4 possible modulation types, BPSK, QPSK, APSK, 16QAM, that use a softmax activation function. This function takes the network's raw scores and converts them into clear probabilities for each class, so the output confidently indicates the likelihood of the signal belonging to each modulation type. The class with the highest probability is then chosen as the network's prediction. Simple as that, well, conceptually.
Okay, that makes sense. Now, an interesting design choice they made was to progressively reduce the number of filters in the convolution layers by a factor of 2 as the network goes deeper. So if you start with, say, 64 filters, the next deeper layer is 32, then 16, and so on. Why this specific choice? It seems counterintuitive, maybe, to reduce the feature extractors as you go deeper. Wouldn't you want more of them to capture more detail?
Yeah, you'd think so, perhaps. But this design choice is quite clever and serves a dual purpose in terms of efficiency and learning effectiveness. Firstly, reducing the number of filters with depth significantly helps in reducing the total number of trainable parameters in the model. Fewer parameters mean a lighter, more efficient model that requires less memory and is faster to train and deploy, which is crucial for real-world wireless systems. Secondly, and perhaps more profoundly, by having fewer filters in the deeper layers, the network is
Implicitly encouraged to extract and retain only the most essential abstract features of the data. The earlier layers might capture fine-grained, low-level details, but as the signal
let's talk about the real star of the ResCNN, its modified residual block. What exactly is a residual block in deep learning in general, and then why is the modified part so important here, especially for untangling those complex NOMA signals? It feels like a significant innovation.
That's absolutely the crux of their ingenuity. To understand the modification, we first need to understand traditional residual blocks. These are a hugely common and powerful technique in deep learning, especially when you're trying to build very deep neural networks with many, many layers. The core idea is simple, but revolutionary. They include skip connections or shortcut connections. What these do is allow information, specifically the output from an earlier layer, to literally skip over one or more
subsequent layers and be directly added to the output of a later layer. This direct path helps to mitigate a major problem known as the vanishing gradient problem, where the signals used to update
no explicit activation in their skip paths. This means the information flowing through the shortcut remains unchanged in its linear representation. The key innovation in the MRB, however, is the deliberate and strategic use of a RILU activation function within the skip path itself, specifically with the one-by-one filters.
Okay, so putting a ReLU in the skip path, why does that seemingly small change matter so much, particularly for NOMA?
It matters a lot. By introducing nonlinearity via ReLU directly into the skip connection, the residual block gains the crucial ability to learn more complex nonlinear features even through these bypass paths. In a NOMA system, where signals are superimposed and often heavily corrupted by interference and noise, the ability to capture these intricate nonlinear patterns is absolutely vital.
A linear skip path might miss subtle but important characteristics of the superimposed signals, almost like trying to pick out a specific instrument in a complex orchestra using only a simple volume knob.
Fascinating. Can you describe the internal structure of this modified residual block a bit more? It sounds like it's doing something quite clever with parallel pathways, almost like it's processing the signal through 2 different lenses simultaneously.
It really is a clever design, employing what we call a parallel architecture. The modified residual block features 2 parallel convolution layers, each designed to produce 16 filters as output. One of these paths is what we call the main path, and it uses larger 1/8 size filters.
These filters are responsible for extracting more complex, localized features from the incoming signal data, really digging deep into the signal patterns. The parallel skip path, on the other hand, uses much...
Yeah, they sound tiny, but the role of that one-by-one filter in the skip path isn't really to extract complex features. Rather, it's a tiny, efficient filter whose main job is to tweak or align the data from the previous step. It ensures that the information coming through this shortcut path has exactly the right size and shape to be cleanly added to or concatenated with the more deeply processed information from the main running path. Think of it as a crucial little adapter, making sure everything fits together perfectly. The outputs from both
parallel paths, each having a shape of RxS by 16, are then vertically concatenated. This means they're stacked on top of each other, merging their learner representations to form a...
Intricate design choices, the number of layers, filter sizes, the specific placement of the modified residual blocks, and those unique real-U activations in the skip path. How were all these minute details and hyperparameters decided? Was it just a painstaking manual trial and error process, maybe involving countless sleepless nights for the researchers?
Maybe some sleepless nights, but not just pure trial and error. While there's always a degree of expert intuition involved in the initial design, the researchers employed a sophisticated and increasingly common tool called ResCNN. This is an automated hyperparameter optimization framework. Instead of manual trial and error, which would indeed be incredibly time-consuming and prone to human bias, ResCNN systematically searches through a predefined range of possible values for parameters like the number of layers, the size of filters, learning rates, and so on.
It performs many experiments in an automated fashion, evaluating the performance of different configurations against the specific problem of modulation classification. This meticulous...
So they've meticulously designed this innovative ResCNN and optimized its architecture using smart tools. Now, how do you actually put a system like this to the test, especially for something as complex as NOMA signals? The researchers didn't use real-world signals directly for their initial evaluation. Instead, they generated a massive synthetic data set. Why is that a smart strategic move for early research in such a complex and interference-laden area, rather than jumping straight to live network data? Seems like real data would be better.
That's a good question. Real data is the ultimate test, but generating a synthetic data set first is indeed a very smart and common practice in this kind of foundational research, especially when you're introducing a new model. It allows for complete and precise control over all the variables, which is almost impossible to achieve in a real-world environment. You can precisely control the signal-to-noise ratio, the specific power ratios between users, the exact channel conditions, and the precise modulation types being used.
This controlled environment ensures that any observed performance improvements or limitations are directly attributable to the model's capabilities and design, rather than being obscured or distorted by
So here's how they did it. First, raw data was modulated using randomly selected modulation formats from a predefined set M, which included 4 common types: BPSK, QPSK, APSK, and 16QAM. This was done for both the far and near users, and the modulated symbols were then normalized to unit energy, ensuring a fair comparison regardless of initial power. Next, these signals were mathematically combined according to the NOMA system model, specifically using equation 1 from the paper to accurately simulate
the actual superimposed signal that would be received at the near user's end. This is where the NOMA interference characteristic was introduced.
So they're recreating that signal pileup mathematically.
Exactly, and crucially, they varied key parameters to simulate diverse real-world conditions. The power ratio, PFPN, between the far and near users, which directly impacts how much stronger one signal is than the other, and the number of time samples n in each signal, controlling the length of the signal snippet the network sees. This allowed them to test the model's robustness under different signal lengths parameters, from a very noisy and challenging -10 dB
all the way up to a very clear and ideal 20 dB with steps of 2 dB in between. This comprehensive range covers virtually all real-world scenarios, from a weak signal
signals. That's a truly staggering amount of data. And once they have this huge data set, how did they then train and test their sophisticated model to ensure the results were reliable? You can't just throw it all at the model, right?
Right, you need a proper methodology. They carefully divided this massive data set, dedicating a substantial 60%, that's 480,000 signals for training the model. This is where the ResCNN learned to recognize the patterns of different modulation types. The remaining 40%, 320,000 signals, was kept strictly separate for testing how well it performed on unseen data. This is crucial for verifying the model's generalization capability, making sure it didn't just memorize the training examples. The model was trained over 50 epochs,
meaning it went through the entire training data set 50 times to learn and refine its internal parameters. They used a batch size of 500, which defines how many samples are processed at once.
That's the standard for this type of task, and helps the model learn to correctly classify between the different categories by minimizing the difference between its predictions and the true labels.
Okay, a very thorough process. So after all that rigorous training and meticulous setup, how did the ResCNN actually perform? What were the key metrics for success, and what kind of accuracy numbers did they achieve? Did it live up to the hype?
Well, the primary metric for success was, as you'd expect, classification accuracy simply, how often the model correctly identified the modulation type. And what's truly impressive here is how well the proposed ResCNN performs under different conditions, showcasing its remarkable adaptability and strength in varying signal environments.
Let's discuss the effect of SNR on accuracy first. It's generally intuitive that as signal quality improves, classification accuracy should go up. Did the ResCNN follow?
Classification accuracy of over 95% for SNR is higher than ADB.
95% above ADB. That sounds pretty good.
It's a remarkably strong result, yeah. It indicates the model's robustness and reliability even in moderately noisy conditions, which are very common in real-world wireless environments, especially in busy urban areas or at the edges of network coverage.
And what about the impact of the number of samples then? Did having more data points for each signal help, or was there a point of diminishing returns? My intuition says more data is almost always better, but is there a trade-off?
You're right, more data generally does provide the model with more information to work with, leading to better classification. So yes, increasing the number of samples in a signal further improves the accuracy. However, as you suspected, this comes at the cost of increased computational complexity because the network has more data to process for each decision. This raises an important question for practical deployment. What's the optimal balance between achieving excellent classification accuracy and the computational resources required? In a real-time system,
You don't always need absolute perfection if the cost in terms of processing power or latency is too high. This research helps pinpoint where that sweet spot might be.
Right, finding that.
That's a great point to connect back to the NOMA principle. If we connect this to the bigger picture of NOMA, a higher power ratio signifies a larger, more distinct difference in power between the far user signal and the near user signal. Remember, the far user signal is the one the near user needs to identify and then cancel out. When this power difference is larger, the far user signal stands out more clearly against the background of the near user signal. It's just less ambiguous. This makes it inherently easier for the model to distinguish and accurately
classify the FAR user signal, thereby reducing the impact of interference during the crucial classification process. The paper even shows that with higher SNRs, if the power ratio is close to 1,
the NOMA design itself, showing that classification works best when NOMA's power layering is pronounced.
Got it. Now let's look at confusion matrices. These are always incredibly insightful for understanding not just how often the model is correct, but where it excels and where it might still struggle, revealing its specific blind spots or where it gets confused. Looking at figure 5 from the source, what did the overall confusion matrix covering all SNRs reveal about the model's performance for different modulation types? Where did it shine and where did it stumble?
Yeah, confusion matrices are great for that. The matrix for all SNRs shows that BPSK,
being the simplest modulation type with only 2 signal points, was classified correctly an impressive 91% of the time, even across all noise levels combined. That's very strong. However,
this is because at low SNRs, these more complex modulations, QPSK, APSK, and 16QAM, tend to have what we call common constellation points. In simpler terms, when the signal is heavily obscured by noise, the specific signal characteristics that differentiate these modulations become very similar. They start to look alike. Imagine a constellation of stars. BPSK might be just 2 very bright, distinct stars. QPSK might add 2 more, still fairly distinct. But as you get to APSK and 16QAM, you have many more stars clustered
closer together. When you then add heavy fog, which is our noise, to the night sky, it becomes much harder to tell which star belongs to which constellation, or to differentiate between
constellation points still pose a persistent problem for the model, even when the fog clears a bit.
Oh, absolutely. The picture changes dramatically, showcasing the MRCNN's true capabilities when signals are clearer. At a higher SNR, 10 dB, the MRCNN's performance improved significantly. It classified both BPSK and QPSK with a perfect 100% accuracy, flawless. For APSK, there was only a small 4% chance of misclassification, either as QPSK or 16QAM, which are its nearest neighbors in terms of complexity, so that's understandable confusion. And for 16QAM, the chance of incorrect classification
dropped to a mere 6%, mostly misidentified as QPSK or 8PSK. Again, understandable neighbors. This clearly demonstrates the model's robustness and accuracy in clearer
ResCNN stack up against the only previously existing AMC method for NOMA, the cumulative-based or CV method we mentioned earlier. Is it just marginally better, or is there a significant leap forward here? This comparative analysis is crucial for understanding its real-world impact.
Yeah, this is the key comparison, and what's truly, I think, groundbreaking here is that the MRCNN demonstrates a clear and significant superiority, especially at low SNRs. This isn't just a technical win, it's potentially a game changer for real-world scenarios. Think about trying to make a critical emergency call from a remote area with weak signal, or ensuring reliable connectivity in a crowded stadium where interference is rampant. The MRCNN's ability to pull vital information out of that digital mud could mean the difference between a drop connection and a lifeline, making NOMA
practical in places traditional systems struggle. While it's true that at high SNRs, specifically above 0 dB, both methods perform quite similarly well, the MRCNN's ability to maintain
SNR performance is definitely key. The paper also highlights performance with different numbers of time samples n, which effectively means how much signal data the model gets to look at. For lower n values, the MRCNN shows notably higher classification accuracy. Can you give us a concrete example of this efficiency and why that might be a practical advantage in the real world?
Certainly. Consider the scenario with N200 samples and a power ratio of 2, PFPN2. The proposed MRCNN achieved over 90% accuracy at a 10 dB SNR. Now,
To achieve the same level of accuracy over 90%, the cumulant-based CB method required a significantly higher 20 dB SNR. That's a 10 dB difference.
Wow, 10 dB is a huge gap in signal quality.
it really is. It means the MRCNN can achieve comparable high performance with less data or under much worse signal conditions. In practice, this could translate to faster processing times because the model doesn't need to wait for a longer signal snippet to make a competent decision. It could also mean reduced resource requirements for data collection or better performance in scenarios where signal length is inherently limited, like short-burst transmissions in IoT devices or very low latency applications where every millisecond counts. It's simply
More efficient with the data it receives.
Okay, that efficiency sounds really valuable. And if we connect this to the bigger picture, Table I in the paper provides a powerful overall accuracy
pretty clear. It unequivocally demonstrates that the proposed MRCNN model consistently outperforms the cumulant-based method for all the tested pairs of power ratio and n values. This isn't just a sporadic win in one specific scenario. It's a consistent superiority across a wide range of realistic operating parameters, confirming its robustness. For instance, with that same power ratio of PFPN2 and N200 samples, the MRCNN achieved an overall accuracy averaged across all SNRs of 69.19%.
Compared to the CB method's 62.86%. That's a significant improvement of over 6% in overall accuracy, which is very substantial in this field, particularly when
And yes, that's basically what it suggests. It implies that while providing more data, a higher N certainly benefits both models by giving them more information to work with, which makes sense that the MRCNN is particularly adept at extracting valuable information and performing well even with a more limited number of samples. The CV method does improve with more data, and it can eventually catch up to the MRCNN's performance if given enough samples. However, the MRCNN's consistent lead with fewer samples is its defining strength. It means that when
data is scarcer, maybe due to channel conditions or application constraints, or when quick processing is paramount with shorter signal bursts, the MRCNN maintains a more significant lead over
So what does this all mean for the future of wireless communication and for all of us who rely on it every single day? We've taken a really deep dive into the critical yet often unseen challenge of automatic modulation classification in next-generation NOMA wireless systems. We've seen how traditional methods, while effective in simple orthogonal systems, often fell short in the face of NOMA's inherent interference, that deliberate stacking of signals we talked about. We then explored how deep learning revolutionized AMC in those orthogonal systems, and finally how brilliant
researchers are now specifically tailoring powerful AI models like this ingenious modified residual CNN to tackle the truly unique and complex interference challenges of NOMA head-on.
In essence, yeah, this research provides a superior and more robust method for a crucial foundational task, precisely identifying the language of the wireless signal at the receiving end of a NOMA system. It clearly outperforms existing solutions, especially where it matters most in challenging low signal-to-noise environments, like when your phone signal is weak, but you still need to get that important call or message through. Furthermore, its ability to achieve high accuracy with less data paves the way for more efficient, faster,
and ultimately more robust wireless communication systems, which is absolutely critical as we demand more and more from our networks than ever before.
And the paper concludes with
pushing the boundaries of what's possible in wireless communication.
This raises an important question for all of us listening. Consider how these seemingly niche, highly technical advancements like precise modulation classification happening deep down at the foundational level of wireless signals are quietly enabling the incredibly sophisticated and interconnected world we live in. We often take our seamless digital experiences for granted, from instant messaging across continents to downloading movies in seconds. But what other invisible complexities are being solved right now in labs and universities around the globe,
allowing our digital lives from our smartphones to smart cities to thrive so effortlessly and seamlessly? What are the next hidden breakthroughs, maybe just like this?